Hi everybody, we're in chapter 8, 8.4, Polar Bonds and Molecules. Here's a snowflake. I'm sure in Florida we haven't seen many of these. And basically the shape and size of this crystal depends on air temperature and the amount of water vapor in the air at the time the crystal forms. And we're going to see by the end of this section what really keeps the structure of the snowflake so, perfectly crystallized. Okay, well, first thing we're going to talk about how when you create a bond that the electronegativity values determine where the electrons spend most of their time. We call that charge distribution. In other words, something that's more electronegative is going to want electrons more. You kind of like those greedy elements that want to steal the electrons in ionic bonds, whereas other ones don't want them as much, and so the electrons aren't going to spend as much time around them. We're going to talk mostly about covalent bonds when we talk about electronegativity because some covalent bonds share equally, some do not share equally. And we know in ionic bonds, the electrons are totally transferred. So what determines the type of molecule we have is the kind and number of atoms joined together. The larger a molecule becomes, then the charges can be spread out a little bit more. And then these features can determine the molecular properties. As I said before, we can't determine covalent bonds properties as well as we can determine other types of bonds. And so let's look at this picture of a tug of war. Okay, this tug of war is basically kind of what's going on between the two nuclei, the positive nuclei of the atoms, trying to pull the electrons towards each other. And the one that wins is the one that likes it more. So that's usually the one that's more electronegative. Okay, when you got equal pull, we have what we call a nonpolar covalent. We have a nonpolar covalent bond. And what an example of a nonpolar covalent bond is something like our diatomic molecules. Something like F2, they have the same electronegativity, so they equally want these. So it's kind of like a tug of war that's equally pulling apart. So nonpolar covalent bonds are usually diatomic molecules such as this, but sometimes you'll find some things that are very, very close in electronegativity, so they pretty much are nonpolar covalent bonds. Now, a different type of covalent bond is a polar covalent bond. Now, all this means is it means that the bond itself is going to be wanting to have the electron closer to the nuclei of the more electronegative species. So there we go. We have the more electronegative atom attracts more strongly and gains a slightly negative charge. It doesn't gain a negative charge. It gains kind of a negative charge. Okay, the less electronegative atom then would be a little bit more positive. Okay, I always used to see, if you know who Donnie Marie was, which is a long time ago, they used to sing a song, I'm a little bit country and I'm a little bit rock and roll. Well, I kind of say I'm a little bit positive and I'm a little bit negative. The higher the electronegativity value, the greater the ability of an atom to attract electrons to itself. So things on the upper right side are going to want to bring the electrons to them. Things on the lower left side are happy not to have them spend much time with them at all. Okay, so hydrogen, if we look on table 6.2, has electronegativity of 2.1, and chlorine, right here, has one of 3.0. So the difference is about 0.9. So that means that the difference is significant, so it's going to be polar. Okay, so we're going to call that a polar covalent bond. Okay, and we can draw our hydrogen chloride or hydrochloric acid molecule like this. We use this little funny looking D. It's the Greek letter delta, and that tells us the hydrogen is a little bit plus and the chlorine is a little bit minus. So they're not true charges. It's just because the electrons spend a little bit more time here. So this is a little bit negative and this is a little bit positive. And that will have a role, as we see in this unit, of acting a little bit like a magnet. And as you can see, you wouldn't see something like D plus 2 or delta minus 2. It's always a value less than 1, a full charge, like if it was an ionic current charge. Okay, and I explained that in the last slide. All right, so we know that electrons aren't really in orbitals. They're in electron clouds, according to the modern atomic theory. So what we see here is if we see chlorine, or chloride and hydrogen chloride, we see that big megabrain look to it, okay? So what we've got here is we've got this large area that the electrons spend most of their time, which is very close to chlorine, and this smaller area where they don't spend much time with hydrogen at all. Okay? So instead of being a nice two round circles of the same size, we've got this huge area for the chlorine's cloud where the electrons spend most of their time, the ones that are shared. And what we also do is sometimes when we draw our HCl, we're going to draw this little arrow, and if you look right here, okay, you have a little plus sign. So that tells you, that always goes over the plus, the little plus one, and this one, the tip of the arrow is kind of like a negative sign, that goes the negative. So that tells you you have a polar covalent bond. Okay, so you can either use the little deltas, or you can use this convention. All right, so let's look at a larger molecule. Okay, in this case, we have hydrogen bonded to oxygen. Oxygen is more electronegative, so these two hydrogens are going to have little positive charges, and there's going to be a negative charge here because of this interaction, and a negative charge here because of this interaction. Okay, remember there's two electrons, lone pairs, on the oxygens. So because they're lone pairs, they give the oxygen a little bit of a negative on both sides. Now we could also represent this. This is a little positive, and here's your negative. This is the direction basically between them, showing where the positive and the negative ones are. This does not add up to something greater than 1. It's just the fact that we're talking usually when we write these, the interaction between two of the elements in the bond. Okay? Now, we do have a chart here that kind of shows what type of bond we have. Usually we have anything that is less than 0.4 electronegativity difference. So if we go back at our chart and look at, for instance, oxygen and chlorine. If you formed a compound with oxygen and chlorine, you would be 0.5. That is sort of on the edge of being nonpolar. Okay? If you had a compound, for instance, between chlorine and bromine, that's 0.2. Okay? So in those cases, you could have something that is nonpolar. But usually, most of the things are going to be slightly polar unless they're diatomic molecules. All right, then we have between 0.4 and 1, we're starting to get it more polar. Okay, they're not super polar, but they're more polar. And then between 1 and 2, very polar covalent. And above 2.0, ionic. Now, I remember when I looked at this, if you look at some ionic compounds, the number is usually 1.6, 1.7, greater than 1.6. But there are some things between 1.6 and 2.0 that are still covalent molecules. For instance, like HF is not ionic. It's very polar, but it's not ionic. So we kind of have to look at these with a grain of salt because there's not really these breakpoints. They're kind of like guidelines, and you should know them because that will help you real quickly if you look at electronegativity table, determine if it is polar or if it's ionic. Ionic is kind of easy because if you have a metal and a nonmetal, you definitely know it's ionic. If you have something like HF, which is very polar, they're two nonmetals, so you know it's not going to be ionic. So you can consider that, even though it's quite high, you could consider that as being very polar. As I said, there's not like a sharp boundary between the two things. It's just saying that if your difference is greater than 2, it's more than likely to be ionic. All right, so let's go through each one of these and see, using table 6.2, what kind of bond forms. So we'll look back at the table. So we have N and H, 2.1 for hydrogen, right? And N is 3.0, so it's 0.9, so it's going to be polar covalent. F and F, I don't even have to look at that because F and F is the same thing, so we know that's going to be nonpolar covalent. Calcium and chlorine, we have a metal and a nonmetal. I can look at the table. Okay, so let's look at it. Calcium is here, it's 1. Chlorine is right here, 3. That's 2.0. And that supports the idea that it is ionic because we have a metal and nonmetal. Now let's look at aluminum chlorine. We have a metal and a nonmetal. Okay, aluminum is 1.5. Chlorine is 3. That gives us a difference of 1.5, which tells us it's very polar covalent. Let's walk through this, okay? So D is one of those ones where you're like, it's a metal and nonmetal. It should be ionic. All right, so there's a summary of what we just said. So 0.9, 0, 2, and 1.5 is your difference. So our differences are shown. Also, remember, you're never going to have a negative value. It's always going to be positive. All right, so we're saying, if we look at this, we're saying moderate polar covalent, nonpolar ionic, very polar covalent. Now this is where I might disagree, okay, because we have a metal and a nonmetal. I would say that's highly likely to be ionic, but very polar covalent sometimes means things that are technically ionic. Okay, if you have a polar bond in a molecule, that usually, a lot of times, not all the times, makes the whole molecule polar. Now, that happens because one part of the molecule is maybe a little more negative, another part is more positive. However, we have some things called symmetry. And you notice if we were making those arrows, a lot of times we call those kind of arrows vectors. And if two vectors are in opposite directions, 180 degrees from each other, so if you little math here, all right, if you have one vector going this way and one vector going this way, and they're equal, okay, in size, that's going to equal 0. They cancel out. Okay, if you have a vector going this way and a vector going this way, however, they may not cancel out. So the whole molecule could be polar. This one would be nonpolar. So what those little arrows mean, we create something called dipole. Okay, we have the positive and negative side. So in the hydrogen chloride molecule, the way we drew it with those little arrows, okay, that tells us there's a dipole. There's only 2 atoms, so it's going to be a polar molecule. Okay? So dipole, there's a positive here and a positive here, okay, in the nucleus, and then you've got all your electrons almost all around chlorine. Okay, so if you have some electricity going on, okay, you have an electric field, there's no electric field, you have positive and negative sides of your molecule, there's your hydrogen, there's your chlorine, okay? And they're all mixed up, okay? But then you make this side negative, look what happens to all the positives. They all line up facing this plate and all the negatives face the positive plate, okay? So you can use electricity to orient all of your polar molecules in the direction of attraction. Okay, so as I mentioned, here's an example of the two vectors that are equal and opposite. Carbon is attached to oxygen by a double bond on each side. So it's linear, 180 degrees. So that means the dipole is going this way and the dipole is going 180 degrees in the opposite direction. If this means they're equally balanced when you are playing tug of war, so this is a non-polar molecule. Even though, so the molecule is non-polar, but these bonds are polar bonds. Okay? So these are polar bonds, but the molecule CO2 is nonpolar because the two polar bonds cancels out those polarities because they're going in opposite directions. Now if we look at water, water is a bent molecule. So let me draw that here. So if we have H2O, we have H, O, H, and we have a plus going this way, and a plus that way. So they're not 180 degrees, so they're going to be some other, when we do the math on that, we would find that it would be still polar. So therefore the molecule is a polar molecule. Okay, if I wrote this another way, you can just think of, if you see something like this and there's not anything here, then you definitely know that, you know, things that have lots of electrons already want more. So you see these two electron pairs, you know that's going to happen. The other thing is these electron pairs act as a repulsive force on each other and push these hydrogens down. Okay? So they don't cancel, the molecule is polar. Okay, what's the difference between an ionic bond and a very polar covalent bond? I'm not going to ask you this on plate positive. I just want you to think about it for a second, then we'll go over it. Okay, two atoms will form an ionic bond rather than a very polar covalent bond if the two atoms have a slightly higher difference in electronegativity. A difference of more than 2.0. But there's no sharp boundary between ionic and covalent bonds. Okay, if it's greater than 2.0, it's more than likely ionic. But as I said before, the aluminum chloride is pretty ionic too. Okay, now we're going to talk about attractions between molecules. We've talked about bonds so far. What we're going to talk about now is intermolecular forces. Okay, so this is the term we're going to use, intermolecular forces. They are not bonds per se. They are attractions because of those polarities I've been going over during this presentation. So they're weaker than either ionic or covalent bonds, and they're also responsible for determining whether a molecule is a gas, a liquid, or a solid. Because if they're strong, it's kind of like you have a very overprotective mother, okay? And she won't let you out of the house, okay? That's a very strong polar covalent bond. Or you might be able to do whatever you want, whenever you want. So that is not a very strong force. And so you're not going to spend a lot of time in the house, okay? So that is kind of like what a polar covalent interaction is. Now, the weakest of these forces, every element, even the noble gases, have what we call van der Waals forces. In other words, if you put a bunch of helium together in a container, they stay in that container. They're not really attracted to each other by any electrostatic forces, but there's these van der Waals forces because what happens is the electrons are moving around, and every once in a while the electrons in the atom, okay, so if you have helium, okay, with 2 electrons, and they're moving around the atom. Sometimes the heliums might be really close to each other, sometimes they'd be far apart. So when they're close, this side would be a little bit negative, this side would be a little positive, and then another helium might get attracted to that positive, and so on and so forth. So they might get ordered for a very short period of time. Okay, so they consist of dipole interactions, okay, very weak dipole interactions, and also dispersion forces, okay, because the dispersion forces. Everything has van der Waals forces. Even things that have stronger intermolecular forces have van der Waals forces. So every atom has van der Waals forces with other atoms or molecules. Okay, dipole interactions occur between polar molecules. Okay, they're going to basically be a little bit stronger. So these are not van der Waals forces. These are a stronger intermolecular force. Okay, so if you have HCl, and this side is a little bit positive, and this side's a little bit negative, and then you have another HCl, they're going to line up because this negative is going to be wanting to be near this, and this positive is going to want to be near that. So they kind of form a stronger pattern. They hold each other together. They're sticky. I think of them as Velcro. You know, Velcro sticks things together, and then, you know, it's easy to take them apart. Sometimes it's harder, but that's kind of what I say about dipole. They're like Velcro. They'll stick together. Okay, so here's a picture of the dipole-dipole interactions, all right? So we've got, again, we don't want to really write van der Waals forces here. Okay, the van der Waals forces are not this. Okay, so here's a molecule of HCl, hydrogen, and you see how they all align up with each other and form this kind of structure. It's like Velcro. It's not permanent like an ionic compound, but it makes it much stronger and harder to pull them apart. Okay, dispersion forces. Okay, this is van der Waals forces. It's caused by the motion of electrons, as I showed you. Okay, when the electrons, for instance, in helium, are on one side, it creates a imbalance, and so that's going to attract things with positive charge, and it will create some attraction, but it's really not as strong as attraction. Okay, and there's a more technical way. I'll let you read that yourself. Okay, so of course, the more electrons you have in a molecule, especially a nonpolar molecule, the more chance that you're going to have a stronger dispersion force. So if we look at the halogens, fluorine and chlorine don't have a lot of electrons, and they're gases at room temperature. Bromine have more, and they attract sufficiently to make this liquid at room temperature. And then iodine has a lot more electrons, and so it's a solid at room temperature and pressure. Okay. Now the strongest of the interactions, this is a special case of dipole interactions, is called hydrogen bonding. So things that like have water in it, or water is an example of it. Now the way I tell you, the only things that have hydrogen bonds are they must have hydrogen, oops, as one of the things, all right, and they must have one of these or more of these atoms in it. And the hydrogen has to be attached to one of these. Okay? So I say hydrogen bonds, if you remember ET, phone, home. Okay? So hydrogen bonds only exist when hydrogen is either bonded with fluorine, oxygen, or nitrogen. And again, the number of electrons will increase the strength of the hydrogen bonds. Oops. Okay, so water molecule is the next example. Oxygen is slightly negative. So as I showed you before, what's going to happen with the water is we have HOH. This is a little bit negative, this is a little bit positive. And we have another water, and then oxygen. And it keeps on going. It keeps on going indefinitely. And that makes water really sticky. Now, one of the things it does is water is a liquid, thank goodness, at room temperature. And it, basically everything else in oxygen's group, H2S, hydrogen sulfide, is a gas. And usually as you go up the periodic table, it should actually get, as you go down, you get liquids like we saw with bromine and iodine. But in this case, these molecules of water should theoretically be a gas. But because of hydrogen bonding, they're not. They're liquids because they form this sticky structure, kind of like Velcro. So there's kind of the space-saving model idea of it and how they align themselves. Now, let's go back to that picture. You see these little dotted lines? They represent the interaction, the intermolecular interaction. This is one molecule, this is another molecule. For a hydrogen bond, we draw dotted lines because they're not a bond, like we've learned already. They're not a true bond. They're an intermolecular interaction. It's a strong intermolecular reaction, but it's not a bond. That's very important. Okay, as you can see at the ending, hydrogen bonding always involves hydrogen. Okay, here's a little rule of thumb. It's only 5% the strength of an average covalent bond. So it's not a strong bond. It's like Velcro. It's kind of temporary. It's strong. It will hold, but you can add a little force and it'll come apart. Okay, how does the snowflake take its shape? Well, it's because those hydrogen and oxygen intermolecular forces in water create this nice crystal structure, as I was drawing previously. Why are hydrogen bonds so important? Well, we talked about that, so I'll let you fill that in on Play Pause It. Okay, the properties of water and biological molecules such as proteins, but also remember that the ability of water to be a liquid at room temperature is one of the major properties. And why are they so diverse? Okay, we know some are gases, some are liquids, and some are solids. And if something is ionic or covalent, all ionic compounds pretty much are solid. Covalent could be any of those three things. So if you have a strong interaction, attraction, then they tend to be solid. Okay? Or perhaps it would be theoretically something that should be a gas, but because of intermolecular forces, those Velcro intermolecular forces, it's actually a liquid. And so there it is. Intermolecular forces, or intermolecular attractions, are what determine the solid, liquid, or gas phase of the substance. And also the melting and boiling points. Okay, again, it's going to be harder to melt something or boil something if it has strong attractive forces. Okay, so usually if something is solid, it might only need a little bit of energy to break those forces of attraction. But if it's strong enough, like a hydrogen bond, then it will take a little bit more. So if it's just van der Waals forces, it's going to be pretty easy to break that and melt things. So they'll have lower boiling points and lower melting points too. Now, very unusually, there are some covalent bonds or covalent molecules that have melting points of 1,000 degrees or higher, which is very, very unusual. And what these are called network solids. Sometimes they're called network crystals. And what happens is the individual molecules, okay, are all covalently bonded together. So we're not talking about so much intermolecular forces. We're talking kind of like a covalent molecule that is actually very similar to an ionic matrix. Now, diamond is one of these things. Diamond is all pure carbon, but because of the pressure that it was formed in Earth, it's got very, very compressed, and the carbons started to bond to each other and form these matrices or crystals. And diamond doesn't melt at all. You can heat it and heat it and heat it, but it will vaporize, turn to gas at 3,500 degrees Celsius. Okay, so let's look at this slide because it will tell you a little bit of how ionic and molecular compounds are arranged. Okay, we know, we've talked about this, and I told you how artificial this formula unit is. It's kind of like the molecule in a molecular compound. And I also told you that you need to know this for your chemistry course whenever you take chemistry, but chemists in everyday life usually slip and call them molecules. Okay, bonds are formed from the transfer of electrons from one of the atoms to another. In molecular compounds, they're shared. Types of elements, you usually have a metal and a non-metal, and in a molecular compound, they're non-metallic elements. Ionic compounds at room temperature are going to be solid. Molecular compounds, it depends. Melting point is really high. Melting point, if it's a solid, is usually low. Ionic compounds, most of them dissolve in water. Few don't, but most of them do. It's a mixed bag for molecular compounds. For instance, sugar dissolves in water. A very long chain hydrocarbon floats in water. Okay, something like olive oil. Okay, ionic compounds in aqueous solutions, good conductors. A few molecular compounds may dissolve, and if you have an acid or something like that, you may have a poor conductor, or it's non-conducting totally. Okay, why do network solids take so much more heat to melt than most covalent compounds? That's the thinking question. I'm going to put this on play pause and see what you can come up with on this. Okay, this is because you actually have to break covalent compounds and covalent bonds. They're all through the solid, so it takes a lot more energy to do that. Okay, remember, most of the time you're talking about melting van der Waals forces or maybe some hydrogen bonds, but a network solid is going to be like a matrix. It's going to be very hard to break. Okay, here's some of our things we should know You might want to take these down in your notes. Your definitions, definitely stop the video and take these down. The same with these and these. And that's it. See you next time. Bye.